Hi, I'm Bill Snodgrass. Welcome to this episode of The World Around Us. We're doing another virtual lab. We're doing another heat exchange lab. I think this is the last one I have planned. Heat exchange lab. This one, we're going to find the initial temperature of a sample of ice. And that sample of ice will be introduced into a calorimeter, in which is some water. We'll have the initial temperature of the water. We'll know the mass of the water. We're going to use a graduated cylinder to get the water and pour it in the calorimeter because we want to get approximately 50 grams of water, and then we'll take the mass of it, and a milliliter and a gram is approximately, depending on air pressure, all that stuff. Physics. Calculator. We're going to calculate again. This time we're calculating the initial temperature of the thing that is taking in the heat. So we got the heat loss and the heat gain side. And the ice is going to be taking in heat. So the ice is going to be on the heat gain side. The ice is going to go from some initial temperature to 0, and then from 0 to some final temperature, and there's that phase change in the middle. So the amount of energy gained by the ice will be three things. The MC delta T for the ice, and then the MH sub F, the delta H sub F, the heat of fusion, so mass times 334, and then that water that used to be ice is going to warm up to the final temperature, so there's going to be another MC delta T. The water in the calorimeter has an initial temperature. It's going to go down. It's going to be the one giving off energy, so it's just going to be MC delta T on the water side, on the heat lost side. So let's get started. What do we need to do this? We need a calorimeter, thermometer, water. You can just get it and measure it. The amount of ice that we're using and the amount of water we're using, there's a lab template linked in the description section. And we're trying to stay in a range that we can work with the equipment that we have. So around 50 milliliters of water and 1 to 3 grams of ice, something like that. We're not going to expect to see a huge temperature change in the water because we're using a small amount of ice in there. Because we want all the ice to melt, and we don't want to end up with some situation where the ice didn't all melt or something like that. So we're going to use a small amount of ice and an adequate, abundant amount of water, bring that water temperature down just a couple of degrees, and get all that energy on the upside. So we need to get started. All right, so procedure-wise, we have a calorimeter cap, a thermometer. Then we're going to start by getting some water. That's very simple. So I'm going to get approximately 50 milliliters of water out of the tap, and that's approximately. Put it into the calorimeter, but first, I need the initial mass of the calorimeter. It's over there. All right, as you see, I'm going to try to edit this a little more briskly. Initial mass of the cup, I already wrote it down, 2.16. 2.16 is the mass of the cup. Put the water in the cup, and then I'm going to go take the mass again, and we're going to come back, magic of video. Mass of the cup with water, 53.46. 53.46 is the mass of the cup with water. Magically doing the math. Hold on, I'll be right back. Got my calculator. All right, mass of the water in the cup. The mass of the water in the cup, 53.46 minus the mass of the cup, 2.16. Mass of the water, 51.3 grams. That's what I've got, 51.3 grams. That's how you do it. So get the mass of your cup, put some water in it, get the mass again, subtract. That's your procedure on finding the mass of the water. Initial temperature of the water, stick the thermometer in, take the temperature. What I'm getting as an initial temperature, I am getting 22. So initial temperature of the water of 22 degrees, initial temperature of the water. All right, next step in the procedures is to get some ice. And you want the ice to be dry, not dry ice like carbon dioxide dry ice, but not any water that has already begun to melt on the surface of the ice. And so you can roll your piece of ice in a paper towel or something before you put it in the cup. I'm going to go get the ice, and obviously that's in the freezer. Be right back. All right, I have a small sample of ice in the weighing boat. I'm not going to weigh the ice. I'm going to weigh it off the end because I don't want to waste any time. Here we go. I'm putting the ice into the calorimeter with the water. Ice is in. Ice is in the calorimeter. I'm putting the cap on it, and now we wait. that is the procedures. The last step of the procedure is going to be to take the final temperature and then record that final temperature. Then it becomes math. So give this time to melt. You can swirl it, and you can tell that the ice is still in there. A few minutes should pass. The ice should all melt. So, magic of video. Here's the edit. The ice is all melted. The ice is all melted. I'm taking the cap off the calorimeter. The reason we put the cap on is we don't want the air of the room to infiltrate, and having that infiltration would change the readings. The small amount that was in there, I should have taken the temperature already. The small amount that was in there did affect the results, but in a small way, because the mass of the air is so small, it's going to contribute very little. Likewise, the mass of the calorimeter is like 2 grams, which compared to the mass of the ice is not negligible, but for the purposes of this lab. And then the final temperature that we are reading here is 17 degrees. So this was your procedures and results. This was the procedures and results. Let me put on the screen, here are the things that we calculated from the procedures. Water mass, 51.3, mass of the ice, 2.5. I'm sparing you all the time when I'm doing the calculations. I'm cutting those out. All right, that is the setup. That is the setup in the procedures. We've collected some data, some results. We're going to just kind of inch our way into the conclusion section just a little bit to talk about how you're going to use the data in the calculations. And then if you're doing the lab virtually or doing it in a class, you're ready to go and do it. All right, here we go. Let's talk about a little bit about the math, and then the procedures section will be done. Now that we have collected, here's all the data that we collected. And here, down here somewhere, we'll put the formula. Energy lost equals heat gained. Energy lost, energy gained, all right? And we said that the water in the calorimeter was giving off energy. So we're going to take the mass of the water, which was 51.3, and that's going to go into the equation on the heat loss side. The specific heat for water is 4.128, and then the delta T for the water was 5. The delta T was 5. Didn't write that down. So there's your energy loss side. Now the energy gain side, you're going to have 3 equations over there. They're going to add together, except we're going to have that delta T hanging in the ice, the mass, the MC delta T for the ice. Then we're going to use that delta T for the ice to calculate the initial temperature. So when we plug all the variables in, we get the equation. It shows 2.5 is the mass, 2.09 is the specific heat of ice, delta T is what we're calculating. So we're going to take all those numbers and plug those into the equation, and then we'll multiply the ones that we can. That's going to leave us with 5.225 delta T plus 2.5 times 334 plus 2.5 times 4.128 times 17. And then we're going to get all of our like terms together. We're going to take all of the things that are just numbers, put them on one side, add those all together, subtract as necessary, which is going to leave us with 5.225 delta T equals some number. And then we're going to divide the sum number, whatever it is, by, and you won't have, if you're using different masses, obviously you won't have 5.225. All right, so if you're doing the lab virtually, it'll be 5. All right, that's the math. All right, let's look at the final conclusion and then the discussion. So if you're still watching the video, you must be just, watching the video. Those of you who are still watching the video and you're supposed to be doing the lab in class, or if you're supposed to be doing the lab virtually and you're supposed to be calculating yourself, go on, go back, go away. Delta T. What was delta T? If we do grind out all the numbers, and I'm going to spare you all of me saying divide and add and this. Here we go. If we add all the numbers together, we get a delta T of 9.3. All right. If the delta T is the final temperature minus the initial temperature, or the initial temperature minus the final temperature, depending on how you want to handle that, we end up with the initial temperature was below the final the zero that we use for the final temperature for the ice, because the ice went from some number to 0. So we're going to subtract the 0 and the delta T. It's going to be that the initial temperature is the negative delta T. So we can conclude that the initial temperature of our ice sample was negative delta T, negative 9.3. Now, if my refrigerator really doesn't go to 9.3 negative Celsius, which would be pretty cold, I don't know what the specs on my freezer is. If there is an error, where did that error come from? Where did we get that error? So the discussion section of the lab worksheet will say, what are possible sources of error? Which is always a good discussion section in any lab you do. Possible sources of error. Well, we did not account for the mass of the thermometer, the mass of the styrofoam cup, or the air in the experiment. So there's several things that were contributing energy to the melting of the ice that did not get calculated into the equation. Also, the limits of the thermometer being no decimal places on this thermometer, just the whole hashes. So interpreting between lines is iffy. So there's some error that is inherent. If you want to get super picky, you could discuss that there was some energy gained by the ice before we put it in the cup when we transferred it from the freezer to the calorimeter. So there was some energy gain there. So those are sources of error. All right, so that brings us to the end of the video. We have found our calculated initial temperature of the ice sample, and we've done a bunch more math, and we've tried to make this a little bit more rapidly edited video. Thank you for watching. Please click the like button, subscribe to the channel, sign up for notifications, leave me a comment, question, or suggestion. If there's a virtual lab, if you're a teacher or instructor somewhere and you have your kids or they're not in the classroom and you're trying to give them some lab experiences, leave me a comment, and I'm willing to try. I'm willing to try to do a virtual lab for you if you have something suggested. That is all for this episode. Thank you for watching. We'll see you in the next one.